Well, welcome back. We're continuing on with non-covalent interactions. I hope to finish that today and talk a bit about the hydrophobic effect, and then we will move on. Instead of drawing bad drawings for you, I'm going to display some images and structures on the computer, and then of course all of this will be available in notes that I will post. I know I am behind on posting lecture video and notes, and I apologize for that. I have no excuse. All right, so as I mentioned in my seminar, one of the interesting things that you learn from a lot of protein structure is that aromatic rings, though in many cases non-polar, can still engage in a lot of interesting non-covalent interactions. And so these are electrostatic potential maps. You can calculate them in Gaussian. It shows you the areas of the surface of each arene, and then basically shows you how much a positive charge would be attracted to various places on the surface of the arene. So the energy of that attraction is shown in color, minus 20 kcals per mole in red up to plus 25 kcals per mole in blue. So a positive charge would be highly attracted to this red spot, but not attracted to this blue spot, whereas a negative charge might be attracted to this blue spot. And so here we have a couple of different aromatic rings. Some of them are present in proteins, like this benzene ring fused to a 5-membered ring with a nitrogen there. It's aromatic. This is called indole. This is just benzene. This is phenol. Here you can see the electronegative oxygen, partial negative charge on it, and so the surface of that oxygen would attract a positive charge. Whereas the proton, which is electron poor and somewhat acidic, is sort of surrounded by a blue space. And then this naphthalene ring, just two benzene rings together. And the reason that aromatic rings are this way is because of differences in electronegativity between sp2 hybridized carbons and hydrogens. So the carbons are electron rich, the hydrogens are electron poor, and therefore the face of the ring is electron rich and the edge of the ring is electron poor. And so in red, you're seeing places where anything that's either a full positive charge or a partial positive charge could interact and have that be stabilizing. So there's a whole host of interactions involving aromatic groups that you ought to be aware of. There's a long history of them, and you'll encounter them mostly today in proteins. However, there's still some people using aromatic rings to develop synthetic receptors for various small molecules and ions, and so these things can be important. So let's see. Did I miss anything about that? So, wait, I want to go back to that. So let's just start with interacting a benzene ring, say, with itself. How do you imagine that interaction would look? Got some ideas, got some options. You just want electron poor stuff interacting and touching electron rich stuff, right? So if the edge of the ring is electron poor and the face of the ring is electron rich, maybe you've got a T-shaped interaction, right? So I'll show you what that looks like. No, that's not it. There we go. Maybe I'll set sphere transparency a little darker. Yeah, I'll just make it 0 so that we can. All right, so you can see this is sort of what we have. If you go back to that electrostatic potential diagram, this is the electron-rich face of one ring, and then the electron-poor edge is packing right into that. This is just one of the lowest energy arrangements. You could imagine it. Well, does it have to be in this particular shape, or could the benzene just be, instead of sort of standing on 2 feet, just standing on one? And yeah, there are a bunch of different configurations that differ slightly in energy. I forget, it was in my talk, but I've forgotten the number, how much this is worth in terms of kcals per mole. I believe it's on the order of anywhere between 3 and 5. So it's decent for a non-covalent interaction. It's worth about as much as a sort of average hydrogen bond. You'll sometimes hear people talk about pi stacking because they've taken a biochemistry class, and in the biochemistry class you have the bases, the purine and pyrimidine bases stacked on each other, and maybe at some point we can go in and look on that. But people have this idea, they misapply that observation in DNA to benzene and think, oh, it would be great for those rings to stack on top of each other. Not so fast, right? If they stack on top of each other, you're going to have repulsive interactions. So if instead you wanted them to stack, instead of being edge to face or a T-shaped sort of dimer, you wanted them to be face to face, they would need to be offset, so that the electron-rich face of one could be sort of hovering under the electron-poor edge of another. And so I'll show you that sort of offset dimer shape here. The effect is subtle, but you can see they're not directly over each other. They're offset a little bit, and that allows for a better, more favorable interaction. Okay, so that's just benzene rings interacting with each other. Basically anything you can think of that's a positive charge or has an electron-poor area of it can engage in an interaction with the benzene ring. So the most famousest of these is the so-called cation pi interaction. So here is a potassium ion sitting down on the face of a benzene ring, and it's within van der Waals contact. They're closer to each other than they should be just based on their van der Waals radii. I can turn the sphere transparency up if you want to see sort of where the atoms are inside there. But this interaction is worth about 18 to 20 kilocalories per mole, because you have a full positive charge interacting with that electron-rich face of the aromatic ring. Now this is potassium, but you could do this with sodium or lithium, and you can calculate based on the size of the ion, how strong and how close it can get to the face of the benzene ring. You can calculate how strong the interaction should be. This kind of thing ends up appearing a lot in protein structures, not only for just single sort of metal ions, but there are also positively charged groups in protein structures that are important. So let's see if I can bring up this other thinking. There we go. Display, setting, rendering, modernize. Oh, already has. Okay, so the identity of this protein isn't important because I don't remember what it's called. But here you're seeing in dark gray the aromatic rings of a tryptophan amino acid, a phenylalanine amino acid side chain, and a tyrosine amino acid side chain. Indole, benzene, phenol. And based on what I showed you from electrostatic, potential surfaces, which I'll just bring up again here, all of these have electron-rich faces where you might expect cations to be able to interact. Why are we not rotating here? There we go. In magenta are side chain groups that are positively charged at physiological pH. This one is lysine. That nitrogen is attached to 3 protons. In crystal structures, you can't see protons, so they're generally not shown. We could pretend we knew where they are and draw them there. But in general, you sort of look at this and say that's a lysine side chain. The pKa of the ammonium here is like 11, so you expect it to be, this group to be positively charged at physiological pH. This is arginine. It would, in its positively charged form, it would have 2 protons here, 1 here, and 2 there, with a positive formal charge shared and delocalized between these 3 nitrogens. The pKa of that's called a guanidinium group when it's positively charged, and that pKa is like 12.5. So again, at pH 7, that's going to be positively charged. And here's the other arginine side chain that's going to be positively charged. And we have here this sort of cation pi sandwich. You have positive charge here, aromatic ring there, positive charge here in between 2 aromatic rings, positive charge here directly over this aromatic ring and sort of near that one. And if you wanted to, you could do mutagenesis studies to try to figure out how much these interactions are worth, but they show up all over the place. And this is kind of an interesting cation ladder. One interesting thing to talk about is if we zoom in on these 2 amino acids. I told you that the nitrogen should be positively charged, right? Because it's an ammonium group. We would draw, here's a carbon and then 3 other hydrogens. And you'd put a positive formal charge on that nitrogen. You with me so far? You can sort of see that? Okay. Then why is it that that nitrogen is not actually pointed towards the ring? What's going on? Go ahead, Heather.
Possibly, so like this interaction is favorable, but it's not very strong.
Okay.
So it could be interacting with something else around it strong.
Okay, that's actually a great point. The interaction's favorable, but maybe not that strong. And notice here you've got a negatively charged glutamic acid, so there's probably a salt bridge here that's also contributing, or at least relating to the structure. One of the things that Professor Dennis Docherty points out, because he's sort of the one that discovered that these interactions were important in biology, he points out that formal charge is electron bookkeeping and doesn't actually tell you where the charge is. So even though we would draw a positive formal charge on this nitrogen, if you, and assigning partial charges is difficult. You can do it through calculations. There's a few different methods to do it, and it's sometimes not clear which is the right one to do it. But even though you put a formal positive charge on this nitrogen, that doesn't change the fact that nitrogen's electronegative, right? And so it actually will pull electron density away from this carbon and from these hydrogens. And so there actually is a sizable partial positive charge on that carbon, and so that's why that carbon is pointed towards the aromatic ring, because that is where a lot of the positive charge is. Okay, so often you will see in cation pi type interactions, you will often see carbons attached to formally positively charged atoms, and the carbon being the one that's near the aromatic ring. And that's just fine because a substantial amount of the positive charge is on the carbon. Okay. what else do we want to say about cation pi interactions? They play an important role in the acetylcholine receptor. Acetylcholine has a trimethyl ammonium group that binds to some indole residues. Let's see, should we look that up? Probably not on the fly. Okay, so let's go back to the other types of interactions you can get with aromatic rings. I just still don't understand why modernize wouldn't be the default setting here. It's kind of dumb. Or I'm dumb for not figuring out how to make it the defaults. How do you spell transparency? Okay. Oh, we wanted 0. That's better. Okay, so we've seen the T-shaped benzene dimer. We've seen the offset stacked dimer. We've seen the cation pi interaction. Got to get, whoa! We need to turn some things off there. Okay. Now, we said that the edge of the ring is electron poor, so you might imagine that an anion could interact with the edge of the benzene ring. And in fact, it can, and there's examples of this in proteins. Here I show you just one example of the acetate anion. This is the conjugate base of acetic acid. And those negatively charged oxygens are pretty close and even within van der Waals contact of the benzene CHs. And that's an example of, what would we even call that interaction? Is it an ion dipole interaction? No. I mean, this is an ion, but benzene doesn't have a dipole. So is it an ion-induced dipole interaction? No, because induced dipoles are transient and benzene's distribution of electron density is stable and permanent. What do you call a non-uniform distribution of electron density that's not a dipole? Anybody know? Sort of bizarre. It's called a quadrupole. Your text points out that point charges look like s orbitals, dipoles look like p orbitals, and quadrupoles look like the dz squared orbital. Something like that. So imagine looking at this benzene ring from the side. Just sort of straight on the side. The edge is electron poor, and then the face of the ring is electron rich. And your text says, well, this sort of looks like a dz squared orbital, but basically, if you have a non-uniform distribution of electron density, but it isn't a dipole, it could be a quadrupole. Now, there are higher order things besides quadrupoles, but none that we need to worry about. Okay, well, so this is an ion quadrupole interaction, but most people don't call it that. They would just call it anion pi. And we've done some research in my lab that shows that these types of interactions can be significant, again, worth about 1 kcals per mole. Another example of a non-covalent interaction involving benzene is where you take one benzene ring and replace the hydrogens with fluorines. So here is hexafluorobenzene. If you replace those hydrogens with fluorines, what do you predict that does to the quadrupole? What should be the character of the edge versus the face of this ring now?
Should reverse it.
Should reverse it, right? Because fluorine's more electronegative than carbon. Remember, the whole thing about the quadrupole in the first place is that sp2 hybridized carbons are more electronegative than hydrogen. Well, we can switch that by replacing the hydrogens with fluorines. This is hexafluorobenzene. I don't have an electrostatic potential surface for this, at least. I've got it, I'm sure, somewhere, but not easily accessible. So here, the edge of the ring would be red and the face of the ring would be blue. And because of that, you can stack these two not quite face to face, but pretty close. It's much closer, it's much less offset than the benzene dimer, because now you have an electron-rich face interacting with an electron-poor face on another aromatic amino acid. Some chemical biologists and protein chemists have taken advantage of this effect by synthetically putting in perfluorinated arenes into proteins, and in some cases that can strengthen the existing non-covalent interactions between aromatic rings and make proteins more stable. The chemist who's done a lot of this is at Boston College. His name is Junmin Gao, and he was a postdoc in Jeff Kelly's group, but has done a lot with fluorinated benzene derivatives. Let's see, does that take all of it? Oh, and then the last one that I think I talked about in my talk, any electronegative heteroatom hydrogen bond can point into the face of a benzene ring and you get a favorable interaction. And we've studied this in my lab. But you could imagine water could do this. People talk about sulfur hydrogen bonds being able to do this as well. Basically, any electronegative heteroatom bonded to hydrogen could engage in an interaction with a benzene ring. Now, we're talking about small potatoes here in terms of the strength of the interaction. I don't know that anybody says that anymore, so sorry. It's a reference, I think, to the fact that in Idaho the potatoes are like enormous. My son came home from fifth grade, and his teacher, they were learning about Idaho for some reason. His teacher had brought these big Idaho potatoes that her grandma had given her or something like that. I'm talking like enormous. We baked that thing, and that was Adam's whole meal. Small potatoes, of course, are the kind you get at the grocery store and aren't as impressive. So these interactions are small, but they can add up to make a difference in terms of how stable protein or a supramolecular system is. All right. So I think that's it for arene interactions. Anything you want to ask about that? Okay. So the last non-covalent interaction I want to talk about before we get to the hydrophobic effect is something called the N to pi star interaction. So this is confusing. So I need to turn off the orbitals if I can figure out how. Hide. Remember, it's 45 and 47 that we got to display. Hide. Okay, so here is the amino acid proline. Here is the carbonyl carbon. Here is the alpha carbon. Here is the nitrogen. Here are the rings. And we've got the nitrogen modified with an acetyl group. This is a model for what proline would look like in an existing peptide chain. If the amino acid were just proline, you'd have an NH here that would likely be protonated at physiological pH. But for this particular example, we want to study the structure and conformation of proline as it would be in a protein or peptide chain. So this nitrogen is tied up with an amide. Here's the carbonyl carbon of what we would imagine the subsequent amino acid being. This could be the alpha carbon, and we've just truncated it there with a methyl group. And then on the other side, the carbonyl carbon here, instead of being a carboxylic acid, we've had it be the methyl ester. We could have it be the amide nitrogen, though for teasing out the effect that we want to see here, the methyl ester is actually best. Okay, so we talked about proline recently, and we talked about how because the amide nitrogen is attached to two different carbons, it's actually not that different to have the amide bond here be cis versus trans. So this is currently the trans configuration. Here is the bond between the previous carbonyl carbon and the amide nitrogen. Here's what would have been the alpha carbon on this side, and here's the, you can't quite see it, here's the alpha carbon on the other side. They're on opposite sides of this amide bond, so this is the trans configuration. If you were to rotate around this carbon-carbon bond, you'd have the cis configuration. Now, and I told you that the equilibrium constant between cis and trans is close to 1 for proline, though the trans is a little bit more stable. And Professor Rains has studied the reason why, and it appears to be because there is a lone pair on this carbonyl oxygen that is placed just right and pointing just exactly towards the pi star on this carbonyl carbon. Okay, so what do we mean by that? Let me show you the lone pair. Whoops. Hide surface. Oh shoot, I decided maybe that was okay. No, that's the pi bond. What have I done? Okay, hide. I just can't read. That's my problem. Okay. All right, so this is the P-rich lone pair on the carbonyl oxygen. There's a little bit of it back here. Remember when we dealt with the group orbitals on formaldehyde, this is, I think, the pi CH2 minus 2p combination. But notice that that P-rich lone pair is sort of pointed towards where the carbonyl carbon is. I don't know why I'm trying to point simultaneously with my pointer and the arrow. That's kind of distracting. So now I'm going to show you, I'm going to turn off the lone pair, and then I'll show you the pi star associated with that carbonyl carbon. All right, there it is. So if we look at it from the side, that looks like just your regular run-of-the-mill pi star, right? Mostly on the carbon for reasons we've already discussed. Now, if we show both of them, you can see there's actually an area where the two overlap. Can't see it that well, and I'm not sure that Gaussian really does a great job here. It's this area here that's darker. If we want to pretend it maybe looks a little green as the yellow and the blue overlap. But that lone pair is occupying the same space as this pi star. And Professor Ron Rains suggested that this interaction was significant. Okay, so And there's some work he's done that shows that it can be worth, again, about 1 to 3 kilocalories per mole. Now let's make some predictions, shall we? What should happen to the carbonyl carbon? And maybe I'll just turn off the orbitals so that we can not get too distracted. What should happen to a pi bond if electron density is being shared with the pi star? If you dumped the electron density in there entirely, what would happen? Should break the bond, right? And that is indeed what happens when we have a nucleophile attack a carbonyl carbon, right? We'll show the surface again. Here's the LUMO of that associated with that carbon-oxygen pi bond. A nucleophile will come in here from this direction where most of that orbital is. It will tend to approach at about the tetrahedral angle, about 107, maybe 109, with respect to this carbon-oxygen bond. And then as that pi bond breaks, that carbon goes from being trigonal planar to being what? Tetrahedral sp3 hybridized. That's your tetrahedral intermediate in carbonyl attack, right? So if this lone pair were donating electron density into that pi star, you might expect to see the carbon-oxygen pi bond to be a little longer than it would normally be. And you might expect this carbon to not be as planar as you thought it would be, right? You might expect it to be pyramidalized just a little bit. And so you can actually make that measurement. I'm going to turn off the orbitals, except I'm not clicking on the right thing. Oops. And then we'll use the measurement tool in Gaussian. First, we'll look at the angle between this oxygen, this carbon, and that oxygen. It's around 96. That's not quite the angle at which nucleophiles tend to approach carbonyls, but it's close. Next, we're going to look and see how flat that carbonyl carbon is. You can sort of see it from here, right? We're looking straight down the carbon-oxygen bond, and then it looks like the other carbon-oxygen bond back here is coplanar with the carbon-oxygen pi bond. But do you see how that alpha carbon's just a little skewed? Do you see how it's just a little off? We can measure the extent to which this carbon is pyramidal by measuring a weird dihedral angle. So I'm going to click 4 atoms in this order. If it were trigonal planar, this number would be 0, and it's 1.5, which is a fair amount of pyramidalization. We could take actually this other amide bond that's not participating in this interaction and measure its pyramidalization, and what we would see is it's basically 0. So the take-home message is that when this interaction is happening, it's enough to make that carbon just a little bit out of plane with respect to the 3 groups that are surrounding it. All right. And Raines went on to show that this is important. It probably, in his estimation, contributes, he thinks, about as much to alpha helical stability as does hydrogen bonding. That's still somewhat controversial, but he's made one of the many projects that he does. He's studied this for years and looked for these types of things in alpha helices, and they're all over the place. Yeah. So that's one that I think is important enough that you ought to be aware of. And um, yeah, anyway, I don't think I have any more to say about that. Any questions you want to ask? Okay, so let's talk the hydrophobic. We are skipping chapter 4, which is on supramolecular chemistry. It's not that that stuff isn't important and interesting. It's just we probably don't have time for it. And it's a lot of crown ethers binding cations and then some other. Anyway, it's interesting enough, but it's sort of specific enough to that field that I thought we'd do other things. But you should feel welcome to go back and read it and learn more. And we may cover some of it later. So we're going to do chapter 5, which is acid-base chemistry. We're not going to spend very much time there because most of it's review of stuff in 351. Chapter 6 is stereochemistry. We're not going to spend that much time there. And then chapter 7 is kinetics, and there's a ton of stuff in there that's useful. So we may spend quite a bit of time there. I think we have an exam scheduled next week on the 21st. What's that?
The 20th and the 21st.
Is it the 20th and the 21st? Okay.
Wednesday.
Okay. Do you want it to be then? Do you want extra time? I mean, I'm flexible. I'm actually going out of town late next week to a conference, so I won't be around Wednesday or Friday.
Are we still going to have class?
No. I mean, I could get a sub, but I prefer not to. There are two things we might do. I could record lectures, or we could just skip them.
So
Skip them.
If we have an exam next week, it'll basically just be everything covered.
Since the previous exam. So that's, what the heck was chapter 2 about? I can't even remember. Nobody remembers?
Electronic effects.
The carbon cannon.
Oh, yeah. Electronic effects and electronic and steric effects in molecular structure and then non-covalent interactions.
Yeah, non-covalent interaction.
Yeah, I mean, it's a decent chunk. So
When would you move it to?
I'd maybe give you another week. I mean, do you want to deal with it next week or the week of Halloween? And I guess the other question is that we did the exam in writing down on the sheet format. Last year, as I think I mentioned, we did oral exams, which took, I think, a fair amount of time, but some people found useful. The way it would go is I would hand out the exam maybe 2 days before, and then you had to work by yourself, but use any and all resources to answer the questions. And then you had to come to my office and we would talk for like a half hour to 45 minutes. And you would present the answer to one question of your choice. And then I would choose another one and you'd have to talk about it. And I would sort of assess your understanding from that conversation. So we can try that. It will just take time. So I mean, what we would basically need is a Tuesday or a Thursday, and then I would send out a Google Sheet, and you would sign up for a half-hour time sometime during the day to come talk to me. Well, I mean, I can do whatever the heck I want, right? Because I'm in charge. But if you want to try that, I'm willing to give it a shot. I think it's sometimes easier for me to assess your understanding when we can have a conversation than just on paper. So should we try that? Okay, so that means the test will not be on the 20th or the 21st. I'm going to push it back a week. It'll probably be on, let's see, do we need a calendar? Calendar. Yeah, so let's plan on the 26th or the 28th. So what I will do is I will hand out the exam on the 25th, and then you'll have a couple days to work on it, and then I'll open up time on the 28th, and you can come talk to me. And what I'll do in terms of feedback is the same thing I did with your exams this time. I'll take notes during our conversation, and then I'll type up a little assessment, and I'll sort of rate your answers using the same rubric that I used for your written exams. And then you'll have seen it both ways and can sort of decide which poison you prefer, you hate less, I think is the, yeah. Okay. So we were talking about the hydrophobic effect. On the left here, we are sort of drawing what it looks like when a hydrocarbon is on its own. You have transient induced dipole interactions, but they are weak. I should press record. Did I already press? Oh no, we've been recording. We've been live for a while. Goodness, what did I say? Got to watch out for the hot mic. Anyway, the interactions are transient and weak. And because they're weak, there's a lot of disorder. Molecules are moving around without being held tightly to each other. Similarly, in water, we talked about how the hydrogen bonding interactions in water are stronger than the induced dipole interactions in the hydrocarbon solution, but there's a lot of entropy there because the water molecules are constantly changing who's bonded to whom. We switch very easily between a hydrogen bond and a full-on covalent bond. In fact, later on in the acid-base chapter, we'll learn that H3O plus is probably H3O plus and like 6 or 7 other water molecules, which is kind of crazy. So we talked about how in each of those states you've got decent interactions, which is enthalpy, favorable enthalpy, and then you have a lot of entropy. But when you dissolve the hydrocarbon in water, you remove some of the hydrogen bonding interactions that water would have had because the water molecules immediately surrounding the hydrocarbon, there's some space that they can't hydrogen bond with. So oxygen atoms and hydrogen atoms in the immediate vicinity of the hydrocarbon are not fully hydrogen bound. Because of that, the remaining hydrogen bonds will be stronger and those water molecules will be held more tightly in this sort of net or ice-like cage that surrounds the hydrocarbon. And so in other words, in going from like bulk water to water surrounding a hydrocarbon, you've got a fairly substantial loss of entropy. And that's what makes it thermodynamically unfavorable for a hydrocarbon to dissolve in water. Or alternatively, that's what makes it thermodynamically favorable for hydrocarbons in water to separate themselves out and not be dissolved in water. So this is why oil and water don't mix, because if they did, you would have to dramatically reduce the freedom and entropy of water molecules. All right. So I think, any questions about that? It's a fairly important concept. You might hear your 351 students, if you have them, saying things, getting questions about this wrong, saying things like, oh, well, oil and water don't mix because the oil is nonpolar and the water is polar and nonpolar don't mix. And that's just restating the observation. Why is the sky blue? Well, because it's blue, right? No, the real reason is what we've talked about in terms of what it takes to put a hydrocarbon in water and the reduced entropy of the surrounding water molecules. Now, and there are a lot of processes that are driven by this. For example, the formation of micelles is all about getting nonpolar surface area out of water. Formation of lipid bilayers, same thing. And in fact, folding of proteins is in many cases related to getting nonpolar stuff not exposed to water. So if this is an unfolded protein chain, very conformationally flexible, but you have nonpolar groups exposed to solvent. And around each of them, you have this ice-like cage of water molecules with reduced entropy. And we'll zoom in and we'll put one there. And it will be sad because of reduced entropy. That'll make you feel bad. But if the protein can rearrange its conformation such that the nonpolar groups are all on the inside, they will interact with each other on the inside, but it's not that that interaction is particularly strong. It's just that now you have a ton of water molecules that used to be surrounding those nonpolar residues, and we're free. They have maximum conformational entropy now. So this is a hydrophobically driven process. Now, processes that are driven by the hydrophobic effect have a unique thermodynamic signature. And this is a little bit tricky to explain, but I think it's important enough, and some of you may encounter it enough in your future that it's worth talking about. So going from an unfolded state for a protein, and the analogy here would be hydrocarbon in water. Do you see the relationship between those two situations? Before, we have just a hydrocarbon in water. Here we have hydrocarbons attached to protein and it's exposed to the water. And then down here we have the folded protein, and this corresponds to the hydrocarbon being separate from water. All right, and there's a free energy associated with this process, and it's favorable, so we expect it to be negative, meaning it's downhill in energy. And the reason it's downhill in energy is predominantly because of entropy, okay? Because you go from water having low entropy to going to a place where, anyway, afterwards you have high entropy of water. Okay, so that means if this process is favorable and delta G is negative, that means you're at a higher energy here than you are there. All right. You can, for processes like this, there are experiments you can do where you can calculate the enthalpy, and the entropy associated with that folding process. But there's another term in there, and that's the change in heat capacity. Okay, so a little bit of PChem, not too much because I don't understand it, but I don't know if you remember that learning in PChem that the first derivative of enthalpy with respect to temperature at constant pressure, that's where the P comes from, is heat capacity. Heat capacity is how much enthalpy changes with temperature. All right, that's just the basic definition. So let's examine what an alternative way of thinking about heat capacity is. How much heat must I add to increase the temperature of something? Okay, fine. You've maybe learned in junior high or high school that water has a high heat capacity. But let's examine that further, shall we? What is temperature anyway? What does that tell you?
How fast things are
Right, average kinetic energy of the molecules. Okay. So if you want molecules to move faster, you add energy, right? But we've just spent all of chapter 3 talking about non-covalent interactions, these interactions that allow molecules to, well, interact with each other. And they have some energy that allows a complex between two molecules to be more favorable than two molecules separate. What that means is, if for example, you have two water molecules hydrogen bound to each other, this is a simple and dumb model, but if you have a hydrogen bond there and you want to increase the kinetic energy of both of those water molecules, you're going to pump energy in, but the first bit that you pump in is going to have to break the hydrogen bond, and then you can make the molecules move faster, right? So in a lot of ways, heat capacity tells you how much more on top of molecular kinetic energy, how much more interactions you have. Because in order to raise the temperature, you first have to disrupt the interactions, and then you can increase kinetic energy. I'm not sure I said that right. Does anybody want to restate what I said so I can see if it sounds reasonable?
Yeah, I think you're just talking about to increase temperature, you have to increase kinetic energy of the molecule.
That's right. And if you want to increase kinetic energy of molecules, sometimes you need even more energy because you have to break apart the interactions that are holding them together. Yeah. Break apart the non-covalent interactions that are holding them together. Okay, so let's consider the situation before folding and after folding, or before dissolving the hydrocarbon, or rather when the hydrocarbon's dissolved in water versus when it's not. Let's think about the water molecules. I told you that these water molecules have relatively few degrees of freedom, and that their interactions with each other in the immediate vicinity of the hydrocarbon are stronger. So low entropy of water may be tighter hydrogen bonding in what we will call the first solvent shell. In contrast, here, water has high entropy and probably for those water molecules with higher entropy, probably weaker, more transient hydrogen bonding interactions for the liberated water molecules. Okay, let's think about how that would translate into heat capacity. For the unfolded protein, if I want to increase the temperature of the solution, some of the energy I'm putting in is going to have to go into making these molecules wiggle more. And it's hard to get them going because they're hydrogen bond tightly and they don't have a lot of freedom. Think of it this way. How many of you remember learning in high school that in phase changes of matter, for example, when ice is in water, what's the temperature of ice water? Anybody know? 0 degrees Celsius has to be, right? Because until all the ice is gone, all the energy you put in just melts the ice. It can't increase the temperature of the water, right? Similarly here, I told you to imagine the water in the immediate vicinity of the nonpolar groups as being an ice-like layer. So some of the energy you put in to increase the temperature, before it does that, it's got to melt the ice, okay? So you would expect maybe a higher heat capacity here because you have to melt the ice, by which we mean the layer of low freedom water molecules surrounding the nonpolar groups. In contrast, these water molecules that we liberated are now free, and there's so there's no ice to melt. So we expect heat capacity lower because the ice-like layers are gone, and therefore there is no ice to melt. That means that when we go from something that has non-polar surface area exposed to water to something that doesn't, we're going to go from something that's high heat capacity to something that's lower heat capacity. So we expect the change in heat capacity for going from unfolded to folded, we expect that to be negative. In contrast, if you are measuring the heat capacity of going from something that is folded to unfolded, you expect the change in heat capacity to be positive. And you can measure heat capacities for various processes using calorimetry. And in protein chemistry at least, and actually throughout physical organic chemistry, changes that have changes in water that have going from here to here that have negative heat capacity changes are often thought to be due to the hydrophobic effect. Yeah?
Okay, I might be stupid, but the higher heat capacity and then it goes to lower heat capacity, how is that negative if we're going from unfolded to folded? Because like the higher heat capacity, let's say are they negative numbers?
No, the heat capacities are, they,
Because like if the unfolded was 100 and
yeah.
the folded was 25,
Uh-huh.
how would that be negative?
Because you take the final state, 25 minus 100.
Duh. Okay. Yeah.
Okay, that wasn't a stupid question, by the way. There's no such things. Yeah, you see it now. I think heat capacities are usually positive. I can't think of any case in which they're negative, but I could be wrong.
That's what I thought.
But a change in heat capacity can be negative. So if you're doing an experiment measuring protein folding and you see a change in heat capacity as the protein folds to become lower, that's consistent with a folding process that's driven by the hydrophobic effect. Okay. So I think that basically finishes us up on non-covalent interactions. There's a lot more, but I think you've got the foundation to deal with the things that you might encounter.